This talk arose really because I found out in early January last year, about the Megaconstellation Threat, and I was only given a few basic details. And what I heard, horrified, I wanted to get more involved. And Robert Massey, who's the Deputy Executive Director at the RAS, was organising a meeting for astronomers to get together to discuss the threat from these satellites. So I asked to be included, and as I said earlier on, Brian Sheen from Cornwall is also involved on that panel. So moving forwards, we have megaconstellations. What are they? So I'm going to talk about that. Their threat to astronomy in various senses. Now I shall talk a little bit about the geometry and some of the science and so on involved, and a bit about the satellites themselves. But it then also leads on to questions of the safe and sustainable use of space, as well as continued access to space. There is a worry that if we put so many of these satellites up there, how the heck are we going to find a launch window? Then there are some legal challenges to megaconstellations to maybe try and subdue the number that are actually launched. But also, I think, for me, quite worryingly, I enjoy looking at what's going on in the world and world politics, but it worries me that there is a great potential when space is considered to be a resource that will potentially become a battleground where people will fight to claim volumes of space or certain orbits in space, and that there could be certain international tensions raised. So that's what I'm roughly going to cover in the talk. Now, I said earlier on to Fred that this talk will last about 1 hour and 20 minutes. I haven't worked out a way of cutting it down, so I will stop at some convenient point for a 10-minute break, probably about 1 hour in for a 10-minute break, and then finish the last 20 minutes off afterwards. Okay. So it all started back in 1957. The first Sputnik was launched, 4th of October 57. Very simple satellite. And there have been an estimated 8,000 launches up to the point where the Starlink satellites started to launch last year. And again, before the Starlink satellites, getting on for a couple of thousand active satellites. It's a bit difficult to keep this this presentation completely up to date because, of course, he's launching them at the rate of another 100 or so a month. Now, back then, in the early days of satellites, the cost of launching a satellite of typically a big satellite, 6,000 to 8,000 kilograms, was of the order of $100 to $400 million. They were big things, expensive to launch because the launch costs were high. It was new technology. The satellites themselves were big because if you're going to launch a satellite up there and you're going to put it out, for example, into a geostationary orbit as a communication satellite, for example, then it's going to be a big, expensive satellite that's got to have the capability to receive signals from Earth and broadcast signals back to Earth. So satellites in those days were expensive, and it was really only the big corporations or governments that could afford to launch satellites at that sort of cost. Since then, the cost of a launch has come down, especially when you look at SpaceX relaunching or reusing their launchers. And even when in the days when we had the space shuttle, you could launch satellites easily then piggybacked in the back. And the Russians have made a business out of launching satellites on behalf of other countries. Not only that, the satellites themselves have become a lot smaller. The electronics can now be miniaturized. There are more efficient solar panels, so you don't need to have them be quite so big. And it's possible to bring the cost of satellites now down to in the region of perhaps 20 to 100-ish or 150-ish K. When you're launching that satellite as part of a payload along with other satellites. And there was a record set by SpaceX recently for a single launch that launched 143 satellites at the same time. Most of them were Starlink, but there were some others as well. So this is the thing. Now you can launch satellites very, very cheaply. And compared to what it used to be. I mean, to be honest, I haven't got 150k in my back pocket to launch my own, but they are now much more affordable than they used to be. Now, the main use of launching satellites is for communications. And in the old days, satellites were launched into an orbit that was 36,000 kilometers up, long way off, big, powerful transmitters and receivers, large solar panels. But even so, out at that distance, they didn't move across the sky because they're in either a geostationary or a geosynchronous orbit, or they didn't move much if they were in a geosynchronous orbit. And the problem now with some of these new Starlink satellites is that they're in a low Earth orbit where they can see less of the Earth's surface, and therefore you need more of them, which is just as well since the cost of them has come down. So this is where we've moved from the age of big single-purpose satellites into smaller systems of satellites, hence the birth of the megaconstellations. So you could probably think of a constellation as being any system of satellites of perhaps 100, maybe a couple of hundred, something like that. And the megaconstellation is perhaps a few hundred upwards. For companies like, for things like the GPS satellite, for example, you might count that as a constellation. For something like the OneWeb satellites, that's on its way up to becoming a megaconstellation. The Starlink satellites launched by SpaceX are already in the megaconstellation mark, and there's a long way to go yet. He's got permission to launch 12,000 of them so far. So we've got a long way to go, and they definitely will be a ultra mega constellation by the time we get towards the end of that period of time. Okay, so first of all, I wanted to say a little bit about the type of geocentric orbits that you can have. First of all, we've got this one here, which is the high Earth orbit. This is where satellites are launched into orbits out beyond the geostationary or geosynchronous orbits, where they have an orbital period which is longer than 24 hours, which means that from the Earth's point of view, they are in sort of retrograde motion across the sky, even if their plane is inclined parallelish to the Earth's equator. Then there aren't many of those. As I say here, it suggests perhaps about 15 satellites out there. A large number of them are in geostationary or geosynchronous orbits. Now, the difference between geostationary and geosynchronous, if you have an orbit which is coplanar with the Earth's equator, so not inclined at all to the Earth's equator, then a satellite out at this distance of 35,786 kilometers above the Earth's surface. When I talk about altitude here, through this talk, I'm going to talk about distance above the Earth's surface, not distance from the Earth's center. And satellites here they have an orbital period of 24 hours. If they are coplanar with the Earth's equator, in other words, they orbit above the Earth's equator, they will always stay above that same fixed longitude on the equator, which means that if you are, if you've got say a Sky TV installation, you can have a fixed satellite dish because the satellite stays in the same position in the sky as seen from a location on Earth. The difference in geostationary geosynchronous is that geosynchronous relaxes that slightly, and it says, well, maybe the orbit isn't circular, can be slightly elliptical, and maybe the orbit's inclined. If the orbit is slightly elliptical, so that sometimes the rate of orbit around the Earth is slightly faster than 24 hours per orbit, and at apogee, the furthest point from the Earth, it is slightly slower than 24 hours per orbit, then it means that the satellite, if you look at it, if it were not inclined to the equator, it would sometimes appear to advance ahead in the sky and sometimes fall behind in the sky. So that's the effect of an eccentricity of the orbit, is to affect the advance and retard, if you like, relative to the Earth's rotation. The effect of inclination is for the satellite to move above and below the equator. So if you have a slightly elliptic inclined orbit at 35,780 kilometers, it will on average stay above the same location on the Earth's surface, but in practice, it will prescribe a stretched figure of 8, like a kind of Lissajous figure, as it goes above and below, where it moves advance of the Earth, moves up to the top of its orbit, and then retards and comes down again. So this is the effect of the eccentricity. So it's not geostationary because it's not fixed in the sky, but it's still geosynchronous, more or less. The medium Earth orbit is not so widely used. And again, you can see there are fewer of them here than there are of the useful ones at geostationary orbit. Excuse me. One of the advantages here, particularly in the use of this kind of orbit called the Molniya orbit, where you have a highly eccentric orbit, but the orbital period is 12 hours. And the advantage of this is that if you have, for example, a surveillance satellite, that satellite will move up across the top here, and it will move slowly around this part of the orbit where it's close to apogee, and it will very quickly whip around underneath and move up and be slow up here again, which means that if you've got, for example, an American satellite looking down on the Russian continent, then you've got a longer period of time to observe Russia. So it's quite common with the surveillance satellites, military surveillance satellites, to use something like a Molniya orbit. The other thing is that if you have the orbit inclined to the Earth's equator, the bulge around the Earth's equator, the sort of the midriff, if you like, around the Earth's equator, has a twisting effect on the orbit, and the twisting effect on the orbit causes the orbit to twist a bit like a gyroscope. If you've done the thing where you've spun a bicycle wheel and tried to twist it, it causes a twist in the axis at right angles to the direction you're trying to twist the axis. Well, in the same way, it causes the orbit to rotate. If you use an inclination of 63 degrees, 63.4 degrees, it turns out that that angle is just right to prevent precession of the orbit's nodes. So the orbit will stay oriented the same way in space all the time. So the Molniya orbit is a very specific elliptical one used for surveillance. One that will be much more common, and one that is the main subject of tonight's talk, is this here, the Walker configuration. Now, this isn't a single orbit. This mesh here of orbits consists of several orbits, all of the same inclination, but where the satellite orbits, there are several of them, each staggered around the Earth, so that this is one orbit, this is another orbit, this is another one, and so on. So you've got several orbits which do cross over, and they all come to the same highest latitude and the same lowest latitude, and it would be that they will all be at the same or a very similar altitude. So Starlink and others are using the Walker configuration quite a lot, or several versions of the Walker configuration, different altitudes, different inclinations, and so on. So what mega constellations are there potentially in view here? We have Starlink, who started out with a number of satellites here at a lower orbit, 325 to 350 kilometers. Quite a few here at, this is the altitude that they're I think going to tackle next, and they're mostly launching them into this altitude at the moment, about 550 kilometers. But you can see that quite apart from the ones from Starlink, there's also Amazon. They want to put a few thousand up there. Samsung are going to put some up there, with different bands, different radio bands, and also here there's a Chinese one which is going to use optical communications down to the ground. By the time you top these up, if you ignore OneWeb, because OneWeb was a little uncertain at the time this table was drawn up, and also the ones that potentially, there have been rumors of Facebook launching its own satellites. If you ignore those and the link ones at the bottom, even that is 58,600 satellites, which is a lot more than the 8,000 or so that had been launched up until about the beginning of last year. So you can see that the skies are potentially going to get quite crowded. Now, there are going to be others. There will be other satellites. For example, since this slide was produced, the European Space Agency have said that they would quite like to have their own communications network. So you could expect a few more thousand from them. And again, obviously, if you get Facebook and they do launch the ones that they've been talking about or rumored to talk about, we may end up in a situation where in perhaps 15 or 20 years' time, there could be as many as 100,000 or 200,000 satellites in orbit around the Earth, most of those being in a low Earth orbit. So I'm going to talk mostly about Starlink satellites and SpaceX today. Many of the things I'm talking about will also apply to other low Earth orbit megaconstellations. So let's look first of all at the Starlink satellites. They've got permission to launch 12,000, which on here is effectively the sum of these phase 1 and phase 2s that I've shown here. When you want to launch a satellite into space in America, you have to get an allocation of radio frequencies from the United States Federal Communications Commission. In the UK, it would be Ofcom, and other countries will have their own agency. All of those different national agencies allocate frequencies on behalf of the ITU, the International Telecommunications Union, which is a United Nations organization. Now, in principle, I suppose the ITU could turn around and say, oh, no, you can't do that, or you can't make that allocation, and so on. But in general, it is simply an organization, an umbrella organization that rubber stamps whatever the national companies, the national organizations allocate. I suppose they would step in if there were a clash between what one country wanted to do or another country wanted to use. But in order to get Starlink launched, SpaceX had to approach the FCC and get permission to launch. Now, this is for what they call a non-geostationary orbit. So you very often will hear these referred to as NGSO satellite systems. And they got permission to launch, first of all, the first phase 1 batch. And they changed the rules slightly, because initially it was the case with a satellite launch that if you're launching a single satellite or a few satellites, you have to use that allocated radio frequency within a certain time. I forget now, I think it's something like 6 years from launch. Otherwise, the allocated frequencies returned to the pool of allocatable frequencies, and you've lost your chance to get your satellite into orbit without, you'd have to basically reapply again to get permission to launch using that frequency, because you obviously need not only to get information from the satellite back down to the ground, but more often than not, you also need to be able to send commands up to the spacecraft to get it to twist or rotate or adjust its orbit and things like that to command the spacecraft. So because of megaconstellations and how many hundreds, if not thousands, of satellites were going to be launched, they changed the rules slightly and said that you had to have half of them deployed within a certain number of years and the rest of them deployed by another number of years. And you basically were given longer to do the whole lot. So I think it was half within 6 years and fully deployed in 9 years. So the FCC have said that the phase 1 satellites, the initial 4,408, these have to be launched within the first 6 years by 29th of March 2024. Now, given that there are currently nearly 1,400 that have been launched and still about 1,350 that are still active, you can see that he's already well on the way. SpaceX, they're already well on the way to getting a half completion of this number by 2024. And then getting the full number of 4,408 done by 29th of March 2027. There is the second phase here, which is another 7,518, half completed by November 2024 and fully completed by November 2027. So this is the first 12,000 they've been given permission to launch, and they all have to be up there by November 2027. So that's only 6 or 7 years, 7 years away. This is also something that's down here. The phase 3 satellites here are ones that SpaceX have applied to launch, an additional 30,000 on top of the 12,000. So they haven't been given permission yet to launch those. And it remains to be seen if they ever will be. Now, interestingly, if I go back to my previous slide, you can see here that OneWeb initially applied to launch 716 satellites. Whilst they were bankrupt, because you may be aware that OneWeb filed for Chapter 11 bankruptcy because they weren't doing too well, which is in America means effectively that you can defer all the creditors. You have to restructure your business so that you can operate debt-free with a different management structure. And to prove that you can be a going concern. And as part of that process, they applied to be able to launch 47,844 satellites, which is a bold move considering that they were in Chapter 11 bankruptcy at the time. But the cynic in me, I've never known to be one who's been cynical. The cynic in me suggests that maybe the reason they did that is because it made them look more valuable. So if they were going to sell the company to somebody, they'd get more money for it. And so they needed to find some mugs who would shell out money to buy OneWeb, keep it going. And an Indian company called Bharti International bought half of it, and the other mugs were the British government who bought the other half. And part of the reason that they did that, I think, and could argue against it, is that having lost the ability to be involved with the EU's Galileo GPS system, the government were looking for maybe a quick way to piggyback a UK GPS system onto the OneWeb satellites using a company that was already proven, already had launched a few satellites, and so on. So the British government and Bharti International provided the initial money, and there have now been some other investors that have come forward and taken some of the slack in investment that was required. So OneWeb is going to go ahead, but they haven't been granted permission to launch their 47,844 satellites. And having persuaded the investors to part with money, there has been no talk since at all of launching that many satellites. So this shows just the ones for Starlink. So if I go on forward, I want to just give you an idea of the nature of the problem here. If you look at all of the orbits, and I obviously won't list all of the orbits, but there were some listed in that previous table, and you look at smearing these satellites out around those orbits, so you get a feel for how much satellite there is per square degree. Well, this is the graph you come up with. Now on here, it's not per square degree. This is number of satellites per 100 square degrees down here on the vertical axis. And this is the latitude on the Earth's surface. So if you look up at the zenith, if you are at 52 to 53 degrees north, if you look up at the zenith when phase 1 has been completed, then you will see between 0.4 and 0.5 of a satellite per 100 square degrees, which might not seem very much, but don't forget, they don't stay there. They move through the sky. And it could also be that in different parts of the sky, they will appear to be more concentrated. So they may look a little more concentrated down near the horizon. And of course, they may also be brighter in certain parts of the sky than others, but I'll come on to that part of it later on. So just to give you a feel for what 100 square degrees looks like, the square of Pegasus has an area of 207 square degrees. The ball of Ursa Major's Dipper has an area of just under 44 square degrees. And if you combine the two quadrangles above and below Orion's belt, then you're talking about something like 82 square degrees. The solar disk is about 0.2 of a square degree. So that gives you an idea. If you have the square of Pegasus 200 square degrees, you would expect, when the square of Pegasus is up near the zenith, you would expect there to always be one satellite somewhere in that square. 0.4 or 0.5 of a satellite per 100 square degrees, times 2, about 1 degree, one satellite all of the time in there. So this graph shows, if you then add to that the phase 2 with the yellow, and then eventually, if they do get permission to launch the other 30,000, the phase 3. You can see that there are distinct peaks here that correspond to the inclination of the orbit. So quite a lot of their satellites, if I go back to the previous slide again, you can see that quite a few of these have got orbital inclinations near 53 degrees. And certainly some of these down here have got 53 degrees. So that causes a peak at those upper latitudes where the satellite rises up over the equator, comes to the top of its orbit above that latitude, and then starts to descend down. So there will be an apparent concentration of satellites up at the inclination of that orbit, at the latitude that corresponds to the inclination of that orbit. So 53 degrees north is a couple of degrees north of Cornwall. And so you will see some of the satellites passing up north of your location. And you may see therefore some concentration of them in your northern horizon, as well as those passing up and down. Whereas if you have someone up in, say, Edinburgh, those satellites inclined at 53 degrees, looking south, they will see a concentration a little further south. So it depends on the inclination of the orbits. It depends on how many there are in those orbits, at that orbital inclination. And it depends also where you are, what your latitude is relative to those orbits. I might come back to this one later on. Okay. So the Starling satellites, what do they look like? Know the enemy, as they say. So here we've got a whole load of Starlink satellites, folded flat, IKEA flat pack fashion, and stacked up on a set of launch rails. And here we've got the one fairing on the outside, and they've taken away the fairing on the side nearest to you so you can see them inside. Roughly for each white bar here, that is a Starlink satellite. So you can see they are very compact in the way that they've been loaded into there. And currently they are launching them at the rate of 60 satellites at a time. I think that must be more than, there must be more than that here. No, maybe there's just 2 rails, 2 stacks on each side. So there are 60 satellites being launched at a time. Once the satellites are launched, the fairings come away and these satellites are released, and the satellites will then spread out along their orbit. Initially, the satellites are launched into an orbit of 290 kilometers altitude. And then, once the satellites have been proven to be working and reliable in the way that they're working, they then move the satellites up to a higher orbit where they're eventually going to be used. And the reason for this is that at 200 kilometers altitude, there is still enough atmospheric drag acting on the satellite that it would re-enter of its own accord in a space of a week or two, something like that. At 290 kilometers, the atmosphere is clearly very, very thin, but there's still enough to cause the drag. And the reason is that, of course, you may get a satellite that's launched, and it may prove to be completely dead. And if it's completely dead, you can't command it, you can't do anything with it. It's essentially a flying brick. And so, since you can't do anything with it, you allow the atmosphere to do its work and cause it to re-enter. Those that work, what they do is they unfold the solar panels here, roughly a 12-meter long solar panel, about a meter wide, or a couple of meters wide. And so this thing unfolds here concertina fashion. And they have the satellite initially in what they call this open book configuration, where the satellite body is parallel to the solar panel. And they orient it so that it's edge on in the direction of travel around the orbit. Now, the reason for that is that whilst it's at low altitudes, you want to minimize, given that this is a satellite that you now know is working, you want to minimize the drag on it. So you keep it in this edge-on open book configuration, move the satellite to a higher orbit, and once you get on station or far enough up that you can safely neglect the atmospheric drag, it moves into here what they call the shark fin configuration, where the body is at right angles to the solar panels, which is the orientation that it will be for most of its working life. Something that's been added to the satellite in the last few launches, the last half a dozen launches and going forwards, is these visors, which are on the underside of the satellite. And the idea of these visors is to drop down and to shade the underside so that the underside of the satellite isn't exposed to sunlight. And this is done as a potential measure to mitigate the amount of light reflected down to the ground. And I'll come back to that a bit later on. So that's what the Starlink satellites themselves look like. But what do you need on the ground? Well, let me just talk about sorry, I'm getting ahead of myself. Let's talk a little bit about the satellites themselves. The early ones that were launched here, the Starlink version 0.9, had some components that didn't burn up on re-entry, but now they do. Constrained to just using the KU band, and now they use KU and KA. They're very slightly more massive because there are extra components added on. They did try coating the underside of the early Starlink 1.0s. They did coat one of them black on the underside because they wanted to see if it would darken the underside enough that the satellite wouldn't be visible or as visible from the ground. Turned out that as an experiment, not terribly effective. It darkened the satellite by about 0.8 of a magnitude, which is nowhere near enough for mitigating the problem as far as astronomers are concerned. And so this visor has been fitted. So they called that one satellite DarkSat, and now they are all visor sats. The trial is still in progress, but some of the early analysis is that it's still not enough. It's still only about another magnitude. They've discontinued painting them black on the underside because it did cause problems with the heat balance. If you paint surfaces of a satellite black, it finds it a lot harder to radiate heat away, and as a result, there is a risk that it will run at a higher temperature, and that it will, the electronics basically won't last as long. It also doesn't get over the problem that for an infrared astronomer, of course, a satellite that's warmer is actually glowing more and producing more infrared light than a cooler one. So you might satisfy the optical astronomers a little bit, but it doesn't do anything for the infrared, microwave, or radio astronomers. The satellites are all equipped with a Hall effect thruster, so they all carry a gas canister, and that's what they use to thrust the satellite, to control the satellite and keep it on station, to counteract the drag force, for example. But also they use some of the gas to force the satellite to re-enter when it gets to the end of its life, to force it to come down in its orbital level until eventually it re-enters. The satellites have got multiple high-speed beam steerable phased array antennae underneath. Now, all that means is that there are some flat panels underneath that produce several beams that can be pointed down, independently pointed down to different locations on the ground. The panels, so 1 meter by 9, not 2 by 12. What was I saying? Each one has a star tracker navigation system for precise pointing, so the satellites will know how they are oriented. And also, the satellites will have a link to the ground so that they can adjust their orbit to attempt to avoid debris and other satellites. It says here, will eventually have, they have just started now putting inter-satellite laser communications on the satellites. So the idea is that you can have a signal sent from the ground up to a satellite. It can then use a laser to beam the signal to another satellite, to another satellite, to another satellite, until eventually you then go from the satellite down back to the ground again. Bear in mind that these satellites are only 550 kilometers up. Light travels in a vacuum faster than it does in an optic fiber. Typically, the refractive index of glass at about 1.5 means that the speed of light in glass is about 2/3 that of in a vacuum. So the time taken to send a signal from, say, Australia to California is going to be faster than sending it via optic fibers around the Earth, or by a geostationary satellite. Geostationary satellites, of course, a long time, because at 35,000 odd kilometers out, there's quite a delay in the time taken for the signal to get up and be reflected back again. Unlike the geostationary satellites that can see about 40% of the Earth's surface, these satellites down at about 550 kilometers could only see about 4% of the Earth's surface, which is why you have to have so many of them to provide you with the coverage. So that's the statistics on the satellites themselves up in orbit. But we've now got to think also about what's down on the ground. So this is the satellite dish that's going to be provided as part of the startup kit. And at the moment, Starlink are as part of what they call their better than nothing beta promotion. Basically, we don't guarantee it'll work well, but it's better than what you've got if you've got none at all. In order to buy into this, you have to pay $499 to acquire one of these antennae and the router that comes with it. And then it's $99 a month for the broadband. In the UK, you're looking at prices that are probably 450 to 500 pounds, and probably about 80 to 100 pounds a month for the broadband, which, so it's not by any means cheap. However, if you live in parts of Scotland where there perhaps aren't enough masts, enough telephone masts, or some parts of Wales maybe where there isn't the coverage, you may be well prepared to pay this sort of money. I'm based in the middle of rural Norfolk, surrounded by fields, and I'm using a router that has a 4G SIM card embedded in it. So this is working perfectly well for me to be able to talk to you using a telephone mast. It's effectively a router with telephone technology inside it to connect to the telephone network. So I get a speed myself, I get a speed of about 15, 20 megabits a second download and 5 or 6 megabits a second upload. But this Starlink system will achieve better than that, because it will achieve something they're already getting, speeds of 50 to 150 megabits a second, 20 to 40 milliseconds latency. That's the delay in the time it takes for the signal, whereas my latency here is typically 40 to 50 milliseconds. And so in some ways, it will still be a better service than what I'm getting here in Norfolk, where the road that I live on is about 1.5 miles long with 6 properties on it, and they're not going to put optic fiber down my road anytime soon. So this would, if I weren't opposed to it, this would be a good solution for me. The dish that they're providing has been nicknamed Dishy McFlatface, and it has this rather interesting shape of router down here. As more and more satellites are launched, so that there are more of them in the sky at any one time, and as the effectiveness, therefore, of the optical links between satellites becomes more pronounced, the coverage and the reliability will improve. Come on, advance. Okay, so I want to move on now and talk a little bit about some of the other problems that arise from. Have I really been talking for 1 hour and 23 minutes? It's not right, is it? No. Okay.
Not at all. 45 minutes roughly.
Okay, thank you. I started this off ages ago and hadn't realised the time is still running. So this, thanks. The important thing, of course, is that if you're going to launch these satellites up there, you have to be careful to make sure they don't collide with each other. CubeSats, one particular type of small satellite, the basic CubeSat is about 4 inches by 4 inches by 4 inches. And you can have assemblies of these that go together to make up larger CubeSats. Now, a 1 kilometer basic CubeSat traveling at 7 kilometers a second has the equivalent kinetic energy of about 6 kilograms of TNT. So you could well imagine that if one of these CubeSats were to collide with the International Space Station, for example, a 6 kilograms TNT explosion on the outside of the ISS is not going to be particularly welcome. Similarly, if it were to collide with another satellite, there wouldn't be much left of the CubeSat and very little left of the larger satellite that it collided with. Now, you can slightly tell here the difference in mindset between the European mentality and the American laid-back mentality, where they talk about particles that are bigger than 10 centimeters, 1 centimeter to 10 centimeters, 1 millimeter to 1 centimeter, whereas the Americans use bigger than a softball, bigger than a marble, or too small to track. And the numbers are a little different, but you can get a feel at least for the order of magnitudes here involved. And you can see that there's a lot of debris up there. It's not just things like dead satellites. It's also things like rocket boosters that were launched fast enough that they've remained in orbit and haven't had enough drag force on them to bring them down yet. It's also going to be things like the occasional spanner that an astronaut let go by mistake, or it's going to be things like maybe a fleck of paint that's come off a satellite. Maybe there's been a micrometeoroid impact on a satellite and there are flecks of paint that have come off. But there's also debris up there that could have been avoided because there have been collisions. The Russians also at one point did cause an explosion. They fired a missile at a satellite and exploded it in orbit and added a huge amount, sorry, not the Russians, the Chinese, and added a huge amount of debris to space. Now, this is the reason why SpaceX are making claims that Starlink satellites will be able to autonomously avoid other satellites. The satellites will know where they are, they will know where they're going, they know what's likely to be in their way, and so they can automatically adjust their orbits slightly to steer around and reduce the risk of a collision with another satellite. Not just other Starlink satellites, but with other satellites in general. How effective that will be when there are 12,000 of up there, and especially if there are 42,000 of them up there, remains to be seen. Clearly, the risk of collision goes up because you don't know what's going to happen. For example, if you have one of the Starlink satellites dies while it's in service and it can no longer be commanded, maybe its ability to thrust itself fails. So now you've got a satellite in orbit that can no longer be steered. At the moment, the failure rate on Starlink satellites is a little bit concerning because there is a proportion of them that have failed, and maybe more than we would welcome. So SpaceX, of course, is saying, well, still early days. We're still working on the design, and they'll get better. They'll get more reliable. Let's hope so. So as well as collision, there's also explosion. You shouldn't have the satellites exploding. They will have batteries, and batteries, as we know, can overheat and can explode. Maybe an electronic component will fail. Maybe a capacitor or something like that that's got a loose connection may overheat and explode. And of course, you've got compressed gas components. You've got, in this case, the krypton gas cylinders on board the satellite. And maybe you get a micrometeoroid impact that could be enough to rupture that compressed gas cylinder and cause the satellite as a whole to become, the phrase I think I heard used recently when talking about one of the Starship launches, was unintentional disassembly. So we can see that there is a risk from explosion. Now, SpaceX have to provide plans to the FCC, not only on the frequencies they want to use, but also on their plans to deorbit the satellite. Even though the atmosphere is very thin out at 550 kilometers altitude, there is enough drag force there to cause the satellite to spiral inwards and to re-enter within about 5 years. So that's one of the big advantages of a low Earth orbit, is that material in those orbits, whether it's a satellite or debris, will gradually spiral inwards. And the further out you go, the longer it will take for that to happen. So that, for example, if you have a satellite out at 700 kilometers or something like that, it might take 1,000 years to fall in, because its atmosphere is getting progressively thinner the further you go up. And so it takes time to fall inwards, and then gradually the drag gets stronger and stronger and stronger. So it accelerates the inward spiral as it comes down lower in altitude. They have to use some of the remaining fuel to lower the perigee of the orbit, and bear in mind that most of these orbits will be circular, very circular, because what drag there is will work to circularize orbits. They will use the fuel to lower perigee to about 300 kilometers, but maintain the apogee at the upper altitude of 550, or whatever the working altitude is for that particular satellite. That will take some time, because the krypton gas thrusters are very, very, very weak, very, very low thrust. To get the satellite, when it's first been launched, to get the satellite from the 290 kilometer altitude orbit up to 550 kilometers takes 43 days. So it takes a long time for that satellite to slowly spiral outwards up to the 550 kilometer orbit that, for the moment, most of them are being placed in. And similarly, it takes a long time for those satellites to spiral back in again when the thruster is being used as a brake to reduce its energy in orbit and cause it to spiral inwards. But you've also got to make sure that there's enough fuel on board so that it can also use that fuel to make sure that it can avoid other things, other satellites and the ISS and Hubble and so on. As it spirals inwards, it's still got to be able to take evasive action to avoid colliding with other things. They will reorient the satellites so that whereas when they're launching them, they have them in this open book configuration to reduce drag, now they'll do the opposite. They'll have them flat on so that the solar panel is acting like a big sail and catching all the air that it can so that atmospheric drag is maximized. Spin down the reaction wheels, drain the batteries flat, and power them down. And after a short while, the satellite will re-enter, and now they are entirely destroyed in the upper atmosphere. None of this really answers what happens if the satellite dies in service, dies in orbit. They intend these satellites to work for between 5 and 7 years. So depends really on how good the electronics is. You don't know what's going to happen. If you've got, for example, several major solar events, you may end up with the electronics failing prematurely, things like that. They will spiral in, it says, within 5 years, but of course, if they spiral in uncommanded, uncontrolled, then they are potentially able to collide with other things on the way down. So if Starlink do eventually achieve 42,000 satellites in orbit, and I hope not, but there is a possibility that the political pressure in the US means that they get their way. If the 42,000 are launched, you've only got to divide the mean lifetime into 42,000 and work out that they're going to have to deorbit them at the rate of 5 to 700 per month and launch 5 to 700 per month to replace them. Now, at the moment, the Falcon 9 launchers that are being used to launch them are launching them 60 at a time. One of the other things that SpaceX want to do with their Starship booster, the heavy booster, is to launch 400 of them at the same time to obviously maintain this kind of replacement rate. You've then got consideration of things like pollution from the launch vehicles and pollution from the re-entry. All of the rare earth metals, expensive rare earth metals that require a lot of work to dig them out of the ground and are obviously going to become a more and more scarce resource as used in electronics, are being burned up and turned from mineral ore in the ground to useful metal on Earth to metal vapor when these satellites re-enter. Orbit raising and deorbiting means also that at any one time, even if you said you're only going to see roughly half of them, because they are bright enough at 290 kilometers to be able to see them with the naked eye, even if only half of them are visible on the way up to or down from their in-service orbit level, even if you're still going to see 600 potentially bright satellites in the sky. They're going to now, SpaceX has said what they're going to do is they're going to try and orient the satellites, as well as having the visors, they're going to try and orient the satellites so that there is the minimum amount of reflection and glinting off the satellites. But during the time that you're trying to raise them to a higher orbit and the time you're trying to deorbit them back down to the ground, your principal concern is that the drag isn't too great on the way up, or you maximize the drag on the way down. And that's not necessarily the optimal orientation to reduce reflections down to the ground. And also, of course, not only that, but if 600 Starlink satellites will be re-entering the Earth's atmosphere each month, that's 20 per day, somewhere around the world, there will be 20 satellites per day entering the sky. And that means that the number of satellite re-entries will become more significant. And since so many of them are at 53 degrees inclination, that suggests that the number of satellite re-entries that we see above our latitudes will become more pronounced as well. So I'm going to move on now to talk about the space debris and the other risk from it, which is if you have a collision that produces debris, you've effectively turned maybe one small piece of debris colliding with a satellite, or one satellite colliding with another satellite, into a huge swarm of pieces of satellite traveling at high velocity in a similar orbit to the orbit that they'd been following. It may be, of course, some combination of the orbit. If two collide at an angle, you'll end up with a sort of a billiard ball type problem as to which way will the bits go. But you're also going to get some bits re-enter and some bits scattered further out and so on. There'll be a spattering process going on. If they're in low Earth orbit, eventually, yes, some of that debris will be caused to re-enter because of atmospheric drag. But there still could be a spike in debris. And that means that you may, perhaps if you had a major collision between satellites, or maybe you had a collision that produced debris that damaged one or two others, you may end up with a spike in the amount of debris that's in orbit that would make launching more satellites dangerous, and potentially more dangerous as well for people living up there. So I wouldn't want to be on the ISS where there's a hailstorm of space debris traveling at 7 kilometers per second. You will remember the film that came out a few years ago, Gravity, where a Russian missile destroyed a defunct satellite. and the cascade of fragments that that explosion generated destroyed a space shuttle and the ISS. And of course, George Clooney came to the rescue and put everything right. All of the maths that looks at space debris and the risk of, or the potential of, a chain reaction was done by a chap called Kessler, Donald Kessler, who wrote a paper with Claude Palais back in '78. And he had originally done the work looking at the collision of asteroids in the asteroid belt. So he applied the same sort of maths to looking at the collision of satellites in orbit around the Earth. And so it's something of a seminal paper. Okay, so looking now at the radio side of things. So this is not so much of interest, I suppose, to amateur astronomers. There aren't as many radio amateurs as there are optical amateurs. But it's certainly a big problem for professional astronomers. And I have to say that I think the problem for the professional radio astronomers is probably greater than that for the optical astronomers, for whom it will be bad enough anyway. But and I'll come on to reasons for that a little later. But here we've got, you can see here the pink, which is there's a frequencies allocated for astronomy, and there are others. But one of the communication bands that they want to use sits right next here to the radio astronomy allocation. And those of you who do know about radio technology know that not only is it impossible to have a perfect radio beam, you get side lobes where some radio energy escapes out sideways rather than along the main beam. But also you can get side bands where some of the radio energy is at adjacent frequencies rather than concentrated on the main frequency. They're just a byproduct, if you like, of radio technology in general. You concentrate most of your energy in one direction, and you concentrate most of your energy in one particular frequency you want to use, but there's a little bit that escapes other side. So they've said that they're going to try and ensure that there is a gap of 250 megahertz here between this downlink and this radio astronomy band here. But there are others. There's also the band being used to communicate up to the satellites, and another one here for communicating downwards. These frequency bands are allocated by the US FCC on behalf of the ITU. Some of these bands are reserved, as I say, for radio astronomy. But the problem is that this was back in the days when you were looking for things like hydrogen, and clearly that's one particular band that is reserved. And there are some others as well, like water and the hydroxide radical OH and cyanide, maybe. Those particular molecules radiate at their own specific frequencies. Some of those are reserved, but not all of them. And you have the problem as well that if you're looking at an object in deep space, it may well be that it's redshifted. So the emission of radiation from, say, water from a galaxy, from a region of a galaxy that's receding from you, you will find that the lines or the signal being produced by that water is redshifted. So of course it's not in the frequency band that you would expect stationary water to be emitting at relative to your telescope. So it would be rather greedy for the radio astronomers to say, well, we'll have all of that band. You just can't do that. So radio astronomers, to some extent, are used to the problem of having to work around the noise from satellites, and of course from aircraft flying over as well, and also from other interference on the ground. There are problems not only from the interference from satellites, but also problems because some installations on the ground are so sensitive, their dishes are so big, their receivers are so sensitive, that even if the satellite were not intentionally broadcasting anything, the straightforward electronic noise of the electronics working, that noise is enough to be detected. So even if the satellite weren't broadcasting, you can still hear the noise that the electrons are making as they're going through the circuitry. it's very faint, it's there, but of course, very often the energies involved in radio astronomy are incredibly faint, incredibly low energy. So you have to be very sure that a signal that you've picked up is a genuine signal. And now these satellites are going to be a whole load of other potential red herrings that you have to account for when you're doing your analysis. There was some worry that if a satellite passed through the beam of something like the Square Kilometre Array telescope, that the signal would be strong enough to damage the radio receivers. But I have seen an article published in their house magazine by Federico Di Bruno that suggests that maybe maybe the signal wouldn't be quite strong enough to cause that damage. Okay, so we've got. I'll do another 5 slides and then we'll take a break. This is to look at the satellites now from the optical point of view, and there is a certain geometry that goes with the visibility of these satellites. If we look at a satellite, and this is drawn to scale for a 1,000 kilometer altitude orbit, and the Earth, the only thing that's not to scale, of course, is I don't think we've ever seen an observatory that's quite that big. You've got the sun 15 degrees below the horizon, and this would be a light beam that just skims the Earth's surface. So it's illuminated up here, but it's dark down here. The visible satellites here. Now, most professional astronomers, and I suppose amateurs may be a little bit less picky about this, but most professional astronomers consider their active working cone to be 120 degrees, 60 degrees either side of the zenith. They tend not to look further down, although having said that, some observations that need to be made of things down near the horizon may be unavoidable. The problem is you've got some satellites down in this sort of glinting zone down here where you may get a specular reflection off a solar panel. They're trying to avoid it, as I say, with the orientation of the satellites, but it's not always possible. But here, all of these satellites are fully illuminated, and therefore, satellites there will be visible to an observer on the ground. Once the sun's gone further down below the horizon, you may only have part of that cone satellites being illuminated, and the ones here will not be visible. If you're observing in the infrared, of course, and a satellite makes a movement across the sky in that direction, it may still glow a little bit here before it cools down. If you're observing in the radio frequencies, then it doesn't matter where you are. All satellites, the satellites will be emitting, and so the position of the sun makes no difference. So it does depend on where the sun is, and the further the sun is below the horizon, the less likely it is that you will see satellites, or you'll see as many satellites in the sky. So if I just move on now to show this one, I mean, this may be a case of teaching granny or grandpa in these gender neutral times to suck eggs. But this is set for the latitude of Birmingham, 52.5 degrees north. And it shows the northern and southern tropics on the celestial sky. And so if you have the sun here at the upper limit in the summertime, then it's only 14.1 degrees below the horizon. And that means that most satellites will be visible at 1,000 kilometers, according to my previous scale diagram. Most satellites will be visible throughout the night. If, however, in the wintertime, where the sun goes down to be 60.9 degrees below the northern horizon, it means that most satellites will not be visible during the night. So it does depend very much on the angle of the sun below the horizon, which means not only the time of evening or morning, but also what time of year. So if I go on now here, this graph, what this shows is what percentage of the satellites that are up there, if you were to consider them spread out over the sky, what percentage of them would be illuminated versus the elevation of the sun, or the depression of the sun, should we say, if it's below the horizon, for different altitudes. So here you have a satellite at a very low altitude, 290 kilometers, and it turns out that at that low level, if you have the sun, say, 15 degrees below the horizon, only 80% of them will be visible. But it falls off very quickly, so that by the time the sun gets to be about 20 degrees below the horizon, very few satellites in that altitude will be visible. By the time you get out to the higher altitude satellites, you've got to have, even if you have the sun down at, say, 30 degrees below the horizon, you've still got 60% of them visible. And so you can see that, you can see the effect of altitude and how important it is on the geometry of what satellites are visible. So just because the satellites are there, and my excuse me, earlier graph that showed the number of satellites per 100 square degrees, that was the number of satellites that would be up there, not the number that would be visible. So this graph allows you to give some feel for how many of those satellites that are up there can be actually seen. There's also the possibility, I suppose, that you could have a satellite passing in front of the moon or some other body, so that you get a small occultation, but it's transient. It's very transient. So that's so much for the geometry of the orbit, right? So modeling the brightness of the actual satellites themselves is very difficult. They are multifaceted. They've got a range of different brightnesses, different albedos, reflections on the surface. It depends on the cross section as seen with the Sun satellite observer angle. At the moment, some of the satellites at 550 kilometers, or not at the moment, as was before they did DarkSat or VisorSat, were at brightnesses of around 4.2 to 5.9 magnitudes at 550 kilometers. So that made them at visible brightness to the naked eye. If you're in a dark sky site anyway, if you're near a conurbation, you might not see some of the fainter ones. Having added the visor, the brightness now has moved up to around 6.5 to 7th magnitude, something like that. So that in practice now they are below naked eye visibility. But I'm sure you realize that that sort of magnitude, 6th or 7th magnitude, in a telescope or a large pair of binoculars is still not negligible. They will be at brighter magnitudes when their orbits are being raised, and they will be at brighter altitudes on the way down near the end of their life. And you will get glinting off the solar panels near dawn and dusk as well. And there, it remains to be seen how effective the VisorSat eventually turns out to be on the final satellites, and also how effective the realigning of the satellites is to reduce the downward reflections. They're using something called a magnetotorquer, which is 3 big coils at right angles to each other. And what you do is you pass an electric current through these coils, so that the resultant magnetic field reacts against the Earth's magnetic field to provide a slight twist force to the satellite, a torsion to the satellite. So that's how they intend to rotate the satellites without requiring the use of fuel, of gas. So I'll do this one slide now as the last one before we take a 10-minute break. So this table here shows satellites in the sky at different altitudes. I have an extra column in the paper I produced, the FAS newsletter. There's another, I think it's 1,000 kilometer or 1,200 kilometer orbit. If you're looking in the sky, let's suppose it's taken out, if you're looking at 30 degrees elevation above the horizon, and you're looking at satellites in a 550 kilometer altitude orbit, then the distance to those satellites is 992.8 kilometers. So this is just literally the effect of the fact that you're looking at an oblique angle at satellites that are 550 kilometers above the Earth's surface. So that's the distance of the satellites. So given that we know roughly the size of the satellites, that says that they are about 1.9 arc seconds across in the sky. Again, from the geometry, you can work out two figures. You can say if the satellite were to be traveling directly from, say, west to east, south of you, so that it's rising, if you like, in the southwest and setting in the southeast. If you're looking south, so you're looking at its transverse velocity at 30 degrees, then that would be the earlier of these two figures here, 16.5 arc minutes of motion per second. The other figure here, 26.3, is if the satellite is rising up from the southern horizon and coming up straight over your head, then above you over the zenith, it will be traveling at 26.3 arc minutes per second. So this gives you a range of angular velocities across the sky. So what I'm aiming to do here is to try and have a simple way of working out how many satellites you would have passing through a given field of view in a given time. So if you know the density of satellites in the sky, in your region of the sky, and you know the field of view of your observing instrument, and you know how long your exposure is, and you have here the angular velocity of the satellites in arc minutes per second, divided by 60 so that it's in arc degrees per second, then you can work out roughly how many satellites you would expect to see passing through that field of view in that exposure time. Now you can get this figure, rho sat, from the graph I showed you much earlier on. If I can get back to it, this one here. This figure up the side here is effectively the density of satellites in the sky. This gives you the number of satellites per 100 square degrees, so you need to take that into account. So let's go back again. So that's where we get that figure from. Now, so typically if you've got a pair of 10 by 50 binoculars with, say, an 8-degree field of view, and you're doing an exposure, okay, you're looking for 10 minutes through your binoculars, then you would expect to see something like 6 satellites passing through the field of view. Typical amateur telescope, over the course of 10 minutes, you would expect to see 3/4 of a satellite. So you stand a three-quarters chance that a satellite will pass through your field of view. The problem comes for the professionals, particularly something like the Vera Rubin telescope. These are the very large, wide field camera telescopes, 9.62 degrees field of view. And if you were to observe with it for 10 minutes, you would see 7.2 satellites pass through that field of view during your 10-minute exposure. In practice, the Vera Rubin telescope doesn't work quite like that. It takes a very large field picture for 15 seconds, then it takes another picture for 15 seconds, then it moves to another part of the sky and does it again. And it covers the whole of the visible sky for that time of the year, I think in a 3-day period. And its principal use is to make comparisons between the sky now and the sky 3 days ago. So you can see if there's a supernova or a nova or a new comet or a new asteroid or something like that wasn't there in the previous picture. For the large wide-angle telescopes like Vera Rubin, which hasn't even started yet, they're still in construction, hasn't seen first light yet, these satellites are going to be an immense problem, to the extent that they reckon that something like 40% of all exposures of the Vera Rubin telescope will be irretrievably damaged. Okay, so I'm going to stop there, and we'll come back and move on to some of the other problems, particularly for the telescope, a bit more detail on the telescopes and the sensors, and then on to some of the other problems that occur. So if I have a break there for 10 minutes, I'll put this up. this is the slide I'll come back to, and I will stop screen sharing when we come back, because I want to show you a little model I knocked up to just to give you a feel for how many satellites could be launched by Starlink, by SpaceX. Okay.
Perfect. Thank you very much. Yeah, 10 minutes then. Is that okay?
Yep.
Well,
yeah. That. Well, if everybody's back, I'll carry on a bit earlier, but I'm probably not.
okay, so perfect. Well, I'm going to go up and check my telescope because that's ready to start. So everybody make a cup of tea.
So just before 9:30, 25 past 9:30, something like that.
That's perfect. Thank you very much, Mr. Daniels. Perfect.
If anybody here's got questions, I can answer questions as well, but I'll remember to ask the question again later on.
I think you need to get a cup of tea as well, don't you? Oh, I've just been given one, so.
It's not hot, but then when you have pint-sized mugs, you get used to not having hot tea.
Yeah.
OneWeb, incidentally, have bounced back, and they've started launching satellites again. But they're planning on launching some of them in higher orbits, which is not good, because the higher the orbit, the longer they're visible for.
Dr. Paul?
Yes, hi Barry.
Yeah, a little bit of irony here. I used to work at the Gunili Satellite Earth Station. Initially, obviously, SATCOMs was a big thing. And then when the fiber optic submarine cables came in, that started to take the traffic of the big satellite antennae.
Mm-hmm.
Therefore, you know, the SATCOMs sort of tailed off a bit. But so a little bit of irony is this Starlink then could slowly decline the use of fiber optic submarine cables.
Potentially, yes, because they either Starlink or comparable systems could do, because the communication times and the latency is lower. Yes.
Yeah. Yeah.
I mean, you've got the radio signal going out through a few hundred kilometers upwards, then passing through a vacuum as it's bounced around the Earth, with probably only small delays at each satellite, where there are repeaters picking up the laser beam and then transmitting it onwards, and then back down to a receiving station at the other end, and all of that would be less than the 2/3 speed in the optic fiber, and of course the various optical repeaters along the route.
Right. Yeah. What is the latency of, say, if we made a telephone call via Starlink to the States, say the east coast of the States? What would be the latency with Starlink then? Would you have
the early tests, as I showed when I was talking about Dishy McFlatface and so on there, some of the early users have reported 150 megabits per second in terms of data rate, and between 20 and 40 milliseconds. Right,
because I've just finished retiring from a submarine cable down at Senon, and our latency across the Atlantic was about 56 milliseconds.
Yeah.
So it's gonna undercut that then quite a bit.
Yes, of course. I mean, latency is less of an issue if you're only streaming video, if you're watching Netflix or something like that.
That's fine. But I think the big financial companies, obviously latency is their bread and butter, really.
Yes, and of course the other thing is that this was in the early days of Starlink, and with more and more satellites being launched, it means that the latency may actually go down and get nearer to the 20 milliseconds rather than the 40.
Wow. So that's a third of, mind you, our submarine cable is about 20 years old now, and there are faster ones in service at the moment. Yeah. So okay, interesting. Yeah.
It's an interesting consideration that they could be faster. You tend to think that the signal's got to get around the Earth one way or another. It's surely going to take the same, but no, in one it's traveling in a vacuum, in one it's traveling in glass.
Yeah, that's right. Yeah. Yeah. Thanks for that.
Yeah, pleasure. We were looking at the possibility of getting involved with the Americans to set up or get UK amateurs involved in observing these satellites to observe the brightness. So you'd need accurate positional and timing information, and also reasonably accurate brightness information, with a view to determining the brightness profile from the satellite, because obviously if the satellite's in a given position, different observers on the ground will see a different brightness coming off the satellite because of different facets and angles and things like that. And if you can compare that with the orientation of the satellite that SpaceX would know, it may be that we could provide information that would help them to optimize the orientation of the satellites. Even so, of course, you're not going to be able to optimize it for everyone on the ground at the same time. How effective this would be, I don't know. The Americans seem to have gone very quiet, however, and the plan to set this up has stalled rather. But I hope we can resurrect it. SpaceX started out mostly talking to the American Astronomical Society. They wanted a bunch of amateurs to discuss with, so they didn't actually contact the RAS until much later. And when they had the inaugural meeting of the RAS Megaconstellation meeting, it was back on the 31st of January last year, and we had a representative, Patricia Cornwall, no, Patricia somebody, I've forgotten her surname now, who was there, and also a representative from OneWeb. I've got her business card. What's her name? I did have a business card. SpaceX. Cooper. You began with C. Patricia Cooper. And she gave a very good talk, but of course she was being very guarded about things that she said. I asked a direct question because she talked about all of these various, the willingness to mitigate and to work with the astronomy community and so on, and they would keep trying to reduce the brightness. So I asked the direct question. I said, well, after we've tried plan A and we've tried plan B and we've tried plan C, what if you still cannot get these satellites down to a level that's acceptable to astronomers? Didn't answer that one. And some of the things as well, you got the sort of, I don't know, that's commercially sensitive or something like that. Certain things they wouldn't answer. And there was also a representative from OneWeb there. But this was at the time that OneWeb were in Chapter 11 bankruptcy. So we were talking to them, but didn't really expect them to recover. But they got bailed out by our government, for better or for worse.
Paul, the thing that strikes me about this is, I mean, if you were developing a new medicine, you prove each stage before you go into bigger release. It's very controlled, and it's set against very clear criteria. Whereas this seems to be a promise all the way. Yeah.
It's suck it and see. It's you launch a satellite, see what it's like, and okay, we'll tweak it, we'll do this, we'll do that. Some of the satellites that have been launched, I mean, they work on the principle, I suppose, if they're looking at launching thousands or tens of thousands of satellites, then what if it takes a couple of hundred to get the formula right? But the thing is, if they're looking at a problem that cannot be resolved in terms of the brightness to astronomers, and they can't get anywhere close to resolving it, then really they shouldn't have started launching them. But the problem is they have, and there's political motivation, there's military backing, and all those sorts of things. And now they've started selling it to end customers as well. It's very difficult to start trying to get their foot out of the door and close it in their face. It's too far down the line, really. The best we can do is work with them to mitigate. But how effective that will be, I don't know.
And it's purely, the satellite's use is purely communication, purely, you know.
Yes, it is. Although, as I say, the OneWeb satellites, I think the government are quite keen to get a GPS facility on OneWeb. The satellites aren't really designed for it, but as I say, there's some political pressure to provide a GPS, a UK GPS, because of the whole process of Brexit, meaning that we were no longer a part of the EU and therefore couldn't be party to any of the secure aspects of the European GPS system. We can still use it as users because we'll still be able to pick up the signals and use them, but we can't any longer be involved in, for example, the Galileo system. Part of it's going to be encrypted for military use, and we're no longer party to that, even though we design most of it ourselves, the encryption systems and so on. Whether they will achieve the same with OneWeb, I don't know. You've got to know the position of the satellites very, very, very accurately for GPS systems, and OneWeb isn't really designed for that. OneWeb also work differently, whereas SpaceX are going for the end user, so that you or I could sign up and buy a Dish McFlatface and one of their routers, and communicate with Starling satellites directly. The OneWeb satellites are more aimed at the telecoms companies, so that they will sell capacity to British Telecom or Vodafone or somebody like that. So they're aiming at a slightly different audience. You're not going to be able to buy a dish to communicate with OneWeb satellites.
Hi, Paul. It's Kevin Reed. I mean, if we had another Carrington event like the 1859 thing, wouldn't it just, knock most of these things out, and all that vast investment? Are they able to protect them in some way from that, or are they just taking a flyer on it and hoping it doesn't happen?
Could be. I mean, so far, of course, they've been lucky and not had any solar storms that have been strong enough to cause them significant problems. I mean, there are issues that can arise from the state of the sun anyway. In times of high solar activity, the Earth's atmosphere actually swells up slightly, and I don't know if it's heating or charged particles, whatever. The atmosphere swells up slightly. So at the low Earth orbits we're talking about, the amount of drag increases. So they have to work harder and use more of the fuel to keep them in orbit during times of high solar activity. So when you get to solar maximum, for example, the ones that are launched and have their lifetime over the period of a solar maximum will have a shorter lifespan than those during a solar minimum. So that's one consideration. But then, as you say, yes, there are things like the Carrington event. But if we had something like the Carrington event, you may also find that we've got a lot more to worry about than just the satellites, because we may find that half of our power grid's gone down in the UK and across Europe and across the US, and there'll be a lot more to think about. There was a very good talk given, for those of you who may have come to or have seen the talk given by Mark Clilvard at the FAS conference in 2019 at the Institute of Astronomy in Cambridge. One of our speakers there, and his talk was about the effect of the sun on the Earth's power grid. Very, very interesting talk, and quite scary to see how how vulnerable we actually are to those sorts of things. And yes, I mean, it could knock out a huge number of the satellites, which would be somewhat ironic, and take some significant rebuilding.
Right. Yeah. You've mentioned the Americans, but isn't this problem going to be doubled by the Chinese and the Russians? And they're not going to work with the Americans and agree orbits, and like you said, with tensions. So this is possibly the tip of the iceberg, isn't it?
Yes. Well, I come on to that more in the second half of the talk. But
apologies.
Yes. No, that's fine. It's reasonable. It's nice to see everybody's listening. The problem is one where currently there are very few international rules and regulations. There are treaties, but
it's a bit like climate change, isn't it? Everyone knows it's a good thing, but nobody wants to do it
because it costs money.
Costs money, and you lose competitive edge.
Exactly, and they've got exactly the same problem now, since we're getting to the days where access to space becomes much more reasonable, and the costs are going down, and the potential benefits are going up. Particularly when you start to look at potentially the idea of mining some of the moon's surface, or mining asteroids, and all of that sort of thing. And space is being seen as a resource for use rather than something to be preserved and sustained. And the worry is that sort of commercial greed may end up making it difficult to be sustainable in its use. I'm sort of prejudging a little bit of my later part of my talk there, but yeah. Is everybody back? If we're not here, say so. Okay. Shall I start again? I think everybody.
Yes, I would think it's about time, if that's okay.
Yeah. Okay.
Thank you very much.
So this link that you can see on the screen at the moment, this is on my own website. QSoft is my company, and if you put it in, you do need to use capital M, capital C to go and look at it. I'm just about to show you what it looks like. There is another one, incidentally, /moon, capital MOON, which is like a lunar phase simulator. But if I need to stop sharing this so that I can show the other one. Does that show? You should see a picture of the Earth. Okay, right. So this was designed for those that are interested. It's designed to run in the web browser. It uses WebGL or a wrapper around it called 3.js, and it allows you to do 3D graphics. So I've put in here the Earth, and if I zoom in, if I can remember the keystrokes to use. The Earth is rotating. It's a bit slow, but if I could turn up the frame rate, and then go up. So I'm just sort of positioning slightly. So here we have good old Earth, and I've got here, if I turn on here, these are the satellites, the initial 12,000 satellites from phase 1 and 2 in my earlier talk. This is what they look like. I haven't found a way really of scaling the satellites, so that's a variable on my slider here. But you can get a feel here for what 12,000 satellites around the Earth looks like. And they look like they're going in all sorts of directions, but if you follow an individual one, you can see it does rise here to 53 degrees latitude and start to fall down again. And there are some in a higher inclination up here. And you can see also that there is this concentration up above, sadly, above our latitudes. So these satellites here are passing over or will be passing over our heads. If he gets permission to launch the other 30,000 satellites, then it will look like that. And you can see as well that here the altitude, typical altitude of the phase 3 satellites, if he gets permission, will be lower down at the 350-ish kilometer altitude. Therefore, more work required to keep them on station because of the extra drag. But you can see that the atmosphere here becomes, the number of satellites becomes much denser at this point. If I turn those off again and sort of zoom in, there is another issue which is more obvious. If I look sideways here, you can see that if you were in an orbit that was sort of around here, you can see that if I turn the satellite size down again, as I say, I haven't found a way of making them scale. But you can see that there are regions, if you're in a satellite up in orbit, so we're looking, I'm thinking here of the Hubble Space Telescope or some others, you can see that looking in certain directions, you may actually be looking through quite a concentration of satellites in the sky, and there have already been some comments where the HST's images are being ruined, especially because one of the advantages of the HST is that you can have very, very long exposures and very difficult to deal with satellites flying through the field of view. You can see the Earth rotating here. So this is just to give you a feel for what the number of satellites will look like. Let's turn the animation off and close that down. Okay, go back to my presentation. Okay, should be back to that and screen view. I've lost one of my windows. There it is. Right. Okay. So moving on. How will this affect professional astronomers? Well, there are things like gamma ray bursts and fast radio bursts that will be harder to detect. Having these satellites passing through the field of view of your telescope or your radio telescope are going to make it much harder to detect transient events. High Z supernovae and wide field and all sky surveys, particularly the ones that use these cameras, these large survey cameras, they're going to be particularly affected. The large statistical effects surveys, all of these are going to be affected. And one of the functions, of course, of these telescopes is to look for things like near Earth asteroids and comets, in particular maybe asteroids that could be on a collision course to Earth, with Earth, and it's going to make it much harder to be able to detect those asteroids early enough to maybe do something about it. And distant solar system objects, if you're looking for very faint objects out at the very edge of the solar system and you're still having these satellites passing through your field of view, it's going to make it much harder to see them. So just as an example of what the problem is here, this is an example of the Vera Rubin telescope. It's a simulation of what it will look like. And here you can see a picture showing not only the saturated streak of a satellite passing through the field of view, but also you've got artifacts produced by the structure of the sensor, if you like, and the excess of electrons produced in a particular area produces artifacts elsewhere, ghosting images, as well as I said earlier on, if you take a picture and then move to another picture, where it was saturated in the first picture may also cause a ghost in the second picture. And given that that's the way the Vera Rubin telescope works, by taking 2 pictures at a time, if there's a saturated streak in the first one, you may see a ghost in the second one. So they need to dim the satellites by some considerable amount, about between 4 and 8 magnitudes, to be able to get these satellites down to the point where you can process out the streaks left by these satellites. And this is 4 to 8 magnitudes compared to the 4th or 5th magnitude when they didn't have the visor. So you're talking about getting these satellites down to perhaps 9th magnitude or something like that, or fainter. And at the moment, there doesn't seem to be any way they can get these satellites down to those sort of levels of brightness. I mentioned here, this is drawn to scale. You've got the surface of the Earth. You've got satellites here up in 540, 50, 60, 70 kilometers altitude here, with a blow up of that in this box. And the Hubble Space Telescope orbits between these dotted lines here, that altitude range. So if you could imagine the telescope here looking sideways, telescope here between the lines looking sideways, you can see that it's also going to be looking from this point, looking out through all of these other satellites here, these layers of satellites. So Hubble Space Telescope is going to be compromised, but also there are other satellites, CHEOPS and WISE, ESA and NASA satellites respectively, and they potentially will be compromised as well by all of these satellites in a low Earth orbit. So those people who say, oh, well, the days of astronomy on the Earth are over anyway, need to bear in mind, of course, that it's not necessarily going to be a straightforward job if you've got these satellites out in orbit, because some of their observations, even made by space telescopes, could be affected by all of these satellites. Depends on the altitude of the observatory and the altitude of the satellites, of course. And to some extent also things like the Sun Satellite Telescope angle, as well, as to whether you're looking at the back side of the satellite with it being illuminated on the other side and so on. Although you're probably not going to point a telescope towards the sun that much. But the point being that it's not just ground-based telescopes that will be affected, but quite possibly space-based ones as well. And so here in summary, the satellites don't have to be illuminated. If you're observing in the infrared or sub-millimeter radio, then you've got a problem because the satellites themselves are producing emissions. SpaceX did say that one of the things they would try and do is that for radio installations, they will try and program the satellites to steer the beams around to avoid radio astronomy sites, so that they don't cause a problem. That doesn't get over the problem that there are side lobes to all of these beams, and so the side lobes may be significantly strong, or maybe strong enough to affect radio astronomers' observations. And of course, redshifting of sources can move the frequencies. And satellites that are illuminated by the sun will have a thermal lag even after they've moved into the shadow, and so they will glow a little, even though they're no longer illuminated. So the problem isn't just the optical one, it is also very much the radio and other wavebands as well. Now, for amateur astronomy, you've got generally smaller instruments and smaller fields of view than professional telescopes, usually, not always. Amateurs often don't take as long an exposure as professionals, but again, there is some overlap there. And amateurs are more likely to use off-the-shelf DSLRs attached to the back of the telescope, although again, some amateurs, such as Fred, have CCD sensors also that they can use. So it would be interesting to look and see whether, for example, the noise levels that are produced could be affected by cooling or things like that. But in general, I think you may find a CCD sensor. You may be able to use software to process the trails out. there have been some other thoughts. Maybe you can use a software application, and there are some already available, to predict when satellites will pass through the area of sky that you're observing, so that you can time your observation to not be interfered by the satellites. And there's also potential here for those who are of an engineering bent and into software as well, to connect that predicted visibility of satellites, connect that with some sort of software or hardware shutter, so that you can effectively close the telescope's eye while the satellites pass over, and then open up again when the satellites have gone, so that you continue tracking, obviously, and you only lose a few seconds of exposure. Beam steering isn't a solution for amateurs, because SpaceX are probably unlikely to steer beams away from Joe Soap on the outskirts of Manchester with his radio telescope in his back garden. Even though they would do it perhaps for Jodrell Bank, they wouldn't do it for him. So I think it's not necessarily going to be a solution for amateur radio observatories either. So again, some possibilities here, but there is a market there for someone to design equipment that would be able to do this kind of shuttering. How are the public affected? Well, in the early days, when the Starlink satellites are being launched, there was a lot of quite a fanfare about all these satellites, this string of dots passing across the sky, and I was rather annoyed, because I was quite well aware of this being only the thin end of a very unpleasant wedge, and yet a lot of the local newspapers and the red top newspapers were sort of touting this as some sort of fireworks show, something spectacular to go out and enjoy, not realizing that there will come a time when it potentially could be an existential threat to ground-based astronomy. So the media are becoming more aware of the problem, although I have to say most of their attention is not so much devoted to how it will affect astronomers, but much more to how it will affect the space debris issue. And if you were to look up these days about the issue of megaconstellations, typically it's connected with space debris rather than problems for astronomers. Even if you can bring the satellites down to below naked eye brightness, you will still see them when they're rising up to operational orbit and coming back down again, and obviously on re-entry. So they still will be there, although not to the extent as was perhaps originally suggested by the initial brightnesses that were seen. And one of my worries is that if you spoil the night sky to too great an extent, okay, it spoils our vocational, our interest in looking at the sky. It will put some astronomers out of a job. But there is the risk, of course, that you may have a lot of youngsters who may be put off looking at the sky, or maybe worse, they'll go to satellite business and launch more satellites. But you may be losing young scientists for the future, and maybe young astronomers for the future. So I've got 33 slides altogether. This is number 30, so not far to go. There are two sides to this story. I mean, obviously, looking at this from the point of view of an astronomer, this is a serious threat to carrying out the science of astronomy from the ground. But of course, people, a lot of places around the world don't have internet coverage at all, either because they're in a poor country where their government hasn't invested in the infrastructure, or because it's in a place where it's just too expensive to put the infrastructure there. There aren't enough people to warrant it. It feels a bit like that in Norfolk sometimes. But you could also argue, of course, if the country is so poor they can't afford that, then they're not going to be able to afford the $499.99 a month for the subscription service. So I'm not quite sure that it's going to necessarily be a global solution to internet, but you have to think about it. There are some people out there who don't really give a fig about the astronomy, but they do want the internet. There have been some international treaties over the past few years since Sputnik 1. If you remember, Sputnik 1 was 1957, and the Outer Space Treaty came about in 1967 with later extensions. And the main principle of the Outer Space Treaty was to try to regulate the use of space for weapons of mass destruction, particularly nuclear weapons. If you have to remember, this was right at the peak of the Cold War, and nobody wanted the idea that you could have, for example, a Russian satellite overhead, and at the outbreak of nuclear war, they could drop nuclear bombs on the US from orbit when you wouldn't be able to see them coming, and you wouldn't get the 4-minute warning and all those sorts of things. So there was a lot of thought given to an outer space treaty, and various other things came out of this, that not only would other weapons of mass destruction be prohibited in orbit or on the moon or on other bodies in space, but also it became clear that nobody could claim sovereignty over space, the moon or other celestial bodies. Nobody could land on the moon. Just the Americans planting a flag on the moon didn't mean that they owned it. The exploration and use of outer space will be carried out for the benefit of all mankind. So this was meant to be, therefore, the considering space to be a benefit for everyone. Nations will be responsible for their own activities in space, and nations. So, if there was any damage caused, it was up to them to compensate for that damage. Nations are bound to assist other astronauts in distress. Luckily, that hasn't happened yet. Also, that nations' space installations and vehicles shall be reciprocally open to other countries for inspection. Well, good luck with that. Allowing the Russians to go and inspect an American spy satellite is not very likely. And there is obviously a certain degree of reciprocity in the fact that things like the ISS are now occupied by several countries. And also that all parties would agree to conduct outer space activities openly and in accordance with international law. And in the end, there were 63 signatories to this, including the US and the UK and Russia. The big space players in those early days could see that there had to be some regulation. They tried to do the Bogatar Declaration in 1976. Effectively, what this is that you have countries on the equator, particularly several of the African countries, and saying, well, the problem is that you, America and Russia and so on, you're busy launching satellites into slots in the geosynchronous orbit above the equator, whereas we, a little country, we want to be able to launch our satellites into space. We can't do it yet, we can't afford it yet, but here we are in the Republic of Congo, for example. And when we do, we want to make sure we've got slots reserved for where our satellites will go. So they tried to pass a declaration to reserve the slots above their land, over their territory, so if you like, at their longitude on the geosynchronous orbit, to be their own. It was pretty much universally ignored, this declaration, because there were only, I think, 8 signatories to this, and as I say, everyone ignored it. And in the same vein, along came the Moon Treaty in 1979. The United Nations, seeing that space was going to be an area where there could be future contention, tried to put in place the Moon Treaty to say that the United Nations would retain jurisdiction over the moon and other planetary bodies and the use of space in general. And this, again, was pretty widely ignored. So the United Nations really was trying to put the marker down that we need to have some sort of international agreement for the way that space is used. But as I say, the US didn't sign up for it, neither did Russia. And I don't think the European Space Agency signed up for it either on behalf of Europe. Obama signed an act allowing US companies and citizens to own and sell resources extracted from the moon, asteroids, and other bodies. Now, what that means is that they cannot own the moon, but if you extract minerals from the moon, then you can own what you extract. And the same goes for asteroids. And Trump more or less echoed that kind of thing last year in April when he signed an executive order saying that, again, private companies could claim and recover resources in space. But what is more worrying is that in the statement he made, outer space is a legally and physically unique domain of human activity, and the United States does not view it as a global commons. Now, the phrase global commons is a legal term. It says that it belongs to everyone and it belongs to no one. Nobody can lay claim to any part of low Earth orbit or any part of the moon. And by making this executive order, Trump was effectively saying, we get there first, it's ours. And not necessarily in the sense of ownership, but saying, we get there first, you've got to work around us. We're not going to necessarily be required to play nice with the rest of you. So that's worrying, because at about the same time as he did that, he put the American Space Force into effect. And I'll come to that in the next slide. One of the legal challenges that came up is that the FCC that allocates the radio frequencies is an American administration, just like NASA, for example. And for the most part, American administrations have to follow a law called NEPA, the National Environmental Protection Act. And what this act does, it says that if there is going to be an impact on the environment, then that particular administration has got to do a full environmental risk assessment. And clearly that adds to the cost of projects and makes them a lot more expensive. NASA have to do this. If NASA are launching things, they've got to do an environmental impact risk assessment for every launch. And if they want to build a new launch pad, they have to do an environmental impact assessment. NASA are not excused from this. The FCC turned around and said, "Well, we're only allocating radio frequencies," and they got a categorical exclusion, having to obey the legal requirements of the Environmental Protection Act. However, there is also a law in the US from the Council on Environmental Quality that says that all agencies, all of the administration agencies, all of them are required to continually update their policies, to continually review them to make sure that they're up to date. And the FCC, it is being argued, has broken that law because they haven't updated their policies in 30 years. And along have come the megaconstellations, and the FCC haven't updated their policies. And in particular, they haven't updated whether or not they should be bound by NEPA. Because if you're launching that many satellites, you've got more pollution from all the launches, pollution from all the re-entering, and of course, you're polluting the night sky. So there is a move to make sure that the FCC is bound by NEPA, and there are at least a couple of senators who are trying to get this. One of them, not surprisingly, is one of the senators for Hawaii, where the telescopes are. So there is the potential for some legal challenges, but how far people will get with that, I don't know. One of the problems is that SpaceX are already getting military contracts to explore the use of Starlink. There was a trial conducted, for example, to use Starlink to guide both a fighter and a refueling plane, so that the two of them could be brought together with navigational aid from Starlink. There's been some talk about using Starlink to guide the cruise missiles that have been launched. And as I said, Trump created the fourth American force, the US Space Force, whereas before the US Space Force had been part of the US Air Force, they are now a separate, fully fledged fourth force. And they are a military service
27,000 feet in altitude and traveling 530 miles per hour.
Discovery, on at the 180.
On at the 180.
Pilot Jim Dutton now taking over controls of the shuttle for a moment. And that call from Capcom Rick Sturko indicates the shuttle has 180 degrees to go in its turnaround.